example of how to complete the square, especially when there's an a term here, and alongside that we're going to go through the process to derive the quadratic formula, which I find easier when there is an a term. I just prefer to plug it in the formula, but in future math it is important to complete the square. It's our only option for certain applications. Alright, moving along, the first step we want to do is arrive to the form just ax squared plus bx, and any integer, or even if it's a fraction, any rational number, this we need to move to the other side. Okay, so for our example, right, all we're doing is subtracting 1 on both sides to arrive at 2x squared minus 6x equals negative 1. Now, with all variables, it tends to get a little tricky. I did put side note here, a cannot be 0, because if a were 0, this term is gone, this x squared term is gone, and would have a linear function, which would be much simpler. So, this can get a little tricky and confusing with all variables. It's nice to see this example on the left as we go, but when I taught high school, this was an Algebra 1 standard, so you had to know how to derive the quadratic from the general form ax squared plus bx plus c equals 0, completing the square to get the quadratic formula. Alright, so subtract in c. Alright, next step is that we don't want an a term here. Can't complete the square with that. So what we do is we divide every term. This is allowed since it's an equation. Whatever we do on one side, we do the other. Now we have x squared. 6 over 2 reduces to 3 and equals negative 1/2. Using that same process with the general form, right? Divide everything by the a term. Except for now we don't get anything to simplify because it's all variables. So it's going to get ugly for a minute here. Okay, next I intentionally left a little bit of space here. When I complete the square, rather than squeezing things in, I try to remember that I'm going to add something on both sides, right? Both for this general form and this example. And the process of completing the square is first we need to take half of the b term. Okay, after we take half of the b term, we square it, and that is what we will add on both sides. Whatever we get, half of b squared. And this half of b, well, let's go ahead and do it really quick, right? B is negative 3. So when I do half of negative 3, I get negative 3 over 2. So this half of b ends up being this perfect square on the left-hand side. So half of b is negative 3/2. I know that that is what will be my perfect square factorization on the left. Okay, so it's almost backwards. Like we do half of b, that goes here, and then we square it, that goes here, right? So this goes to the next line, and whatever we get squared goes to the previous line. Well, this b term over here, b over a, it's not just b, it's half of b over a, because that is my new b, it's b over a. So we get b over 2a. Once again, this time it's positive, right? So positive b over 2a. Well, I like seeing this b over 2a. That reminds me of the quadratic. Right here. I have a b over 2a. So it's looking good. Alright, wrapping this up. Next step, right, you square that term. Whatever you got for half a b, we got negative 3 over 2. We have to square that. So negative 3 over 2 squared is 9 over 4. That is what we're adding to both sides to complete that square. Well, if you did in fact factor this line, right, it would factor here. But what I'm saying is cheat, and you know that the half a b term will be that perfect square here. Okay, on the general form, now we need to do b over 2a squared, right? So that's b squared, and then 2a squared is 4a squared. So I have to add b squared over 4a squared on both sides to complete the square. Now, this might be much more difficult. This here, if you try to factor to a perfect square, that might be more difficult to see, but you can in fact FOIL this out, right? Square this binomial, and you would end up with this here. Alright. Combining this right side, I have negative 1/2 and 9/4. So negative 1/2 would be negative 2/4, and add 9/4 to that is 7/4, right? So 7/4. Over here, negative c over a, I need a LCD which would be 4a squared. So therefore I need to multiply the numerator and denominator by 4a, right? Because 4a times c, the negative c, right, is a negative 4ac. But when I already have an a in the denominator, when I multiply by 4a, I now have 4a squared to get this LCD. Right, so they both have 4a squared. Right, so we could combine these two fractions. I'm going to rewrite it with b squared first, and then minus 4ac. Why would I do that? Well, look at this quadratic. Right, that's good. It's coming along. So on the right side here, we now have b squared minus 4ac all over 4a squared. Okay, moving along. Next step in completing the square, we have a binomial squared. We want to eliminate that, so we take the square root of both sides. Right? Same thing over here. Square root of both sides. We do need to include the plus minus. I got a little sloppy, I apologize, but we'll do that in the next step. Right, so when I square root a square, I'm only left with x minus 3/2 equals, remember, taking the square root of a square when there's a variable, we need to include this plus minus, square root 7 over 4. Right, looking at the general form, square root squared, x plus b over 2a equals plus minus square root b squared minus 4ac all over 4a squared. Almost done. It's looking pretty close. Right? Alright, back to this example over here. Well, I want to get x by itself, right? Isolate x. I have a negative 3/2, so we add 3/2 on both sides. And besides simplifying, this example is about done. X equals, now notice square root of 7 over 4, right? Square root 7 over 4 can be written as square root of 7 over square root of 4, which is square root of 7 over 2. I'm going to go ahead and write it like that on this step. So we have a positive 3/2, and we're adding and subtracting a square root of 7 over 2. Moving back to the general form to derive the quadratic formula. Again, we're isolating x. I need to subtract negative b over 2a, both sides of the equation. And again, I'm going to go ahead and simplify this here, right? Numerator, square root of b squared minus 4ac, we cannot reduce that. Common mistake is thinking, oh, I can eliminate this radical with this b squared, but that's not true. We can only do that when we have multiplication. If this were b squared multiplied by 4ac, we could, because then I could separate these radicals. But over here, right, all I can do is simplify this denominator. Square root of 4 is 2, and square root of a squared is a, which is 2a. Again, we could do that here because it's multiplication. And really, I'm thinking square root of 4 multiplied by square root of a squared. But this numerator, I can't do anything. Square root of b squared minus 4ac, which is good as well because, look, I want that in the quadratic equation. X equals negative b over 2a. I only chose to write this first. Well, I guess because it has a nice ring to it when we say the quadratic equation. You could Google stories and songs. I'm not going to sing in this video for you. There's a tune of Pop Goes the Weasel that fits pretty nice with it. Okay, so I simplified this denominator. Last step. Now, technically, there's nothing wrong with writing it like this, right? This can be done. 3/2 plus or minus square root of 7 over 2. However, when you do the, if I were to do the quadratic formula on this example, my end result would look something like this, because I combine the fractions, right? They have an LCD. I could add the numerators. Note that this is two solutions. We have x equals a 3 plus square root of 7 over 2, and then we have an x equals 3 minus square root of 7 over 2. Alright, there are two solutions here. The example's done. The general form, we have one last step as well. They have an LCD of 2a, right? So combine these fractions. Numerators, I have negative b plus minus square root b squared minus 4ac all over that LCD 2a. And there it is, quadratic formula. Okay, so it's up to you in many of the problems. If you're given an option, like this example, we could complete the square, or you could simply plug in a, b, and c into this quadratic, where a would be 2, b would be negative 6, c would be 1, and you should result in the same thing. I wanted to show, though, this quadratic formula isn't some crazy mystical equation that, I mean, I'm sure back then, I mean, these guys were intelligent to come up with this, especially they didn't have a lot of the notation that we have. It was much more difficult to comprehend, but with common notation, again, this was an Algebra 1 standard, deriving this quadratic formula from here.